Hello again. In this video, we're going to go over section R3, objective 4, which is about simplifying radicals. Now, before we actually simplify some radicals, let's get familiar with these 5 properties of radicals. Okay, the first property says that if n is even, then the nth root of a to the n power is the absolute value of a. Now notice property 2 says that if n is odd, then the nth root of a to the n is simply equal to a. Notice that there's no absolute values on the a here. And I want to show you why that's the case. So I'm going to actually start with this one first. Let's say you take the cube root of 2 cubed. Okay, so in this case, n is 3 and a is 2. And of course, n is odd, right? Well, 2 cubed is 8. And then the cube root of 8 is actually 2. And notice that that is the a value that we started with, right? A was 2, and so when I took the cube root of 2 cubed, I did end up with a. Now let's say you took the cube root of negative 2 cubed. All right, in this case, n is 3, and a is negative 2 now. All right, what's negative 2 cubed? Well, negative 2 cubed is negative 8. And it's negative because you have an odd number of negatives here being multiplied together. So you're taking the cube root of negative 8 in this case. But the cube root of negative 8 is obviously negative 2. So you get a back when I take the cube root of negative 2 cubed. A is negative 2 here, and that's exactly what I got here. So notice that you get a in both cases, whether this be a positive number like 2 or a negative number like negative 2. Anytime I take the nth root of a to the n power and n is odd, it doesn't matter whether a is positive or negative, the nth root of a to the n power is a. But that's only true if n is odd. Now let's look at the case when n is even. Let's say you took the square root of 5 squared. Okay, well then in this case a is 5 and n is 2. Now remember, this is square root, so the index is 2. And so n is even here, right? Okay, well 5 squared is 25. The square root of 25 is 5. Okay, so in this case, we do end up with a, because a is equal to 5. Okay, but let's look at so this is with the case when a is positive. Now let's look at the case when a is negative. So let's say you took the square root of negative 5 squared. Okay, okay, so a in this case, a is negative 5, right? A is the base, so it's negative 5, and n is 2, right? The exponent. Okay, so again, n is even still, but now the base is negative. All right, let's see what happens in this case. Well, negative 5 times negative 5 is 25. And then you take the square root of 25, and you get 5, positive 5. But that's not what a is. A in this case was negative 5. So you can't say that you get a back here, because you don't. This is actually the absolute value of a. The absolute value of a would be positive 5 here, right? Because a is negative 5 in this case. So I actually have to take the absolute value of that to make sure it's a positive 5. Okay, so notice that you really need to take the absolute value of a. Now, in this case, you wouldn't have to say the absolute value of a since a is positive. But in general, the nth root of a to the n is equal to the absolute value of a whenever n is even. And that's because of the concern about a being a negative base. If a is negative, then we can't say that the nth root of a to the n is simply a. It's actually the absolute value of a. Okay, so I just want to make you aware of that distinction. Okay. All right, so let's go back and look at some of the other properties. All right, so the third property says the nth root of a times the nth root of b is the same as the nth root of a times b. So it doesn't really matter what order you do this in. You can take the nth root of both of these first and then multiply them, or you can multiply a and b together first and then simply take the nth root of that number. It's also true that the nth root of a divided by the nth root of b is the same as a divided by b, and then the nth root of that fraction. Okay, and then the fifth property is called the nested radical property. If you take the mth root of the nth root of a, that is equal to the m times n root of a. So for example, if you had the fourth root of the third root of x, that's simply the 12th root of x, because you multiply these two indices to get the index of this single radical. So that's called a nested radical. This is a radical inside of a radical. If that ever happens, you can simply multiply the indices of the radical and write it as one radical where you've multiplied the indices together. So this would be the 12th root of x, because 3 times 4 is 12. Okay, so let's talk about what it means to be a simplified form of a radical. There's actually 4 conditions that we have to be a simplified form of a radical. The first one is the radicand has no factor other than 1 that is a perfect nth power. And so what this means is that all exponents in the radicand must be less than the index. So I think that's the key to remember here. All the exponents in the radicand must be less than the index. Second one, no fractions may appear in the radicand. Third one is no denominator of a fraction may contain a radical. And then the fourth one is the exponents in the radicand may not share a common factor with the index. Okay, so I want to go over some examples where we simplify radicals, where a simplified radical is defined by these 4 rules. Okay, so let's start with this one. This radical is not simplified. And why is that? It's because of this first property. So here it says this means that all exponents in the radicand must be less than the index. So if you look at this example that we're looking at now, the exponent in the radicand is a 5, and it's not less than the index. So this is not considered simplified because it doesn't satisfy the first property. So here's how we simplify these. You want to match the number with the number that the index is. So in this case, the index is 3. And so I want the radicand on the inside to be written in powers of 3. So we're going to write this as c cubed times c squared. Now notice you would add exponents here, so this is the same as c to the 5th power. But the reason I'm writing it like this is because you can simplified the c cubed part. In fact, you can break this up as the cube root of c cubed times the cube root of c squared. Those are equal. But the cube root of c cubed is simply c. And so you end up with c times the cube root of c squared. And now you notice that this exponent on the radicand is less than the index. So that's considered simplified. Okay, so let's look at part B. Now what I would do when you have a number inside for your radicand like this is I would go ahead and factor it. You should always factor these numbers inside the radical. So let's try to factor 50 first. So 50 is 5 times 10, and then 10 is 5 times 2. So you can write 50 as 5 times 5 times 2, which I'm just going to write as 5 squared times 2. Okay, so those are the same thing. Now, when you look at the exponents here inside under the radical, you need to make sure that they're less than the index. Now, the index in this case is 2. So 1 is less than 2, so this one's considered simplified. But this needs to be less than that. And so again, we can still simplify this. So I'm going to write this as the square root of 5 squared times the square root of 2. And this can be simplified because that's equal to 5. Okay, and so simplified, it would be 5 times the square root of 2. So again, what I would do is I would always factor the radicand and then make sure that these powers are less than the index, the powers in the radicand. Okay, let's try this one. So let's go ahead. We're going to factor 32. 32 is 8 times 4. And then 8 is 4 times 2. And that 4 is 2 times 2. And this 4 is 2 times 2. So it looks like you could just write this as 2 to the 5th power, because there's 5 2's here. Okay, so I'm going to write that as 2 to the 5th power. Okay, and then I'm going to go ahead and write this x to the 9th power. I'm going to write it as x to the 4th power as many times as I can. So I can do it twice, and that would give me 8 x's here. And there's 9 total, so that means there's 1 left over. And just make sure when you add up these exponents that it adds up to 9. So 4 plus 1 would give me 9. Now the reason I'm writing it as 4 is because this is actually the 4th root. I left the 4 off here. The index is 4 here. So that's why I'm using x to the 4th. Okay, so write x to the 4th as many times as you can. And then I'm going to do the same thing with y. Y to the 4th. And then I'd have 2 left over. And that would add up to 6. And in fact, I could have done this with the 2. So I'm going to go back and go ahead and do that with the 2. So 2 to the 5th, I'm going to write that as 2 to the 4th as many times as I can. And then whatever's left over, there's 1 2 left over. Notice that this exponent adds up to 5. So it's the same as 2 to the 5th. But I want to match this 4 here with the index, okay? So I want 2 to the 4th and then whatever's left over, which would be 2 to the 1st. Okay, then I'm going to break this up. And I'm going to take the 4th root of each of these individually. And then you need to check and make sure that the powers are less than the indices or the index. Okay, So here it's not, so this can be simplified, and this is just 2. This one is 2 to the first power, so that is less than the index. So I can leave that, that's simplified. This one is not, but that's just x. That's just x. This is the 4th root of x. Notice this is to the first power, so it is less than the index. This one can be simplified to y. And then this one, the 2 is less than the 4, so that's okay. But if you go back and look at the rules, there's 4 different rules. Notice this 4th rule says the exponents in the radicand may not share a common factor with the index. And in this case, these share a common factor. Okay, and so this can be simplified as well. They share a common factor of 2, right? And so I'll show you how to simplify that in a second. For now, I'm going to rearrange all this and put the 2 in front. I'm going to multiply these together. And when you multiply those together, you would add exponents. So that's x squared. And then I'm going to put the y up front. So I'm just rearranging the order in which I multiply. And then you're left with the 4th root of 2 times the 4th root of x, but I can put that under the same radical. And then I'm left with, and I'll do that in a second. Let's just write this as the 4th root of 2 times the 4th root of x. But those can be put under the same radical. I'll do that in a second. And then you're left with this 4th root of y squared. Now this can be simplified because they have a common factor of 2. And so let me show you how to simplify that part. So when you have the 4th root of y squared, remember the index, which is 4 in this case, is the bottom number when you write this in terms of exponents. You can always write radicals in terms of its exponents. And when you do that, this index goes on the bottom, and then this power goes on the top. So the 4th root of y squared is the same as y raised to the 2 over 4 power. And the reason I'm writing it that way is because that makes it clear that this reduces to 1/2, right? That's why they can't have any common factors. Because if they have any common factors, then you can reduce this fraction. So this actually reduces to y to the 1/2 power. Okay, and y to the 1/2 power is the same as the square root of y raised to the first power. So that's how this simplifies. Okay, so I'm going to write this as the square root of y. Okay, and then the rest of this, you have 2x squared times y, and then I can put these under the same radical. I mean the 4th root of 2 times the 4th root of x. You can write that as the 4th root of 2 times x. Okay, those are equal. Okay. Okay, and so now this is simplified. Okay. And we can check this, okay? I'll just quickly run through and check. The first property is that the exponents in the radicand must be less than the index. So let's check that. These are all to the first power. And they're less than the index, right? 1 is less than 2, and these ones are less than the 4. So that's satisfied. No fractions appear in the radicand. We don't have any fractions in any of these. No denominator of a fraction may contain a radical. We have no denominators in this problem, so that's not an issue. And then the exponents in the radicand may not share a common factor with the index, and we check that. These shared a common factor, but we went ahead and reduced it to 1/2. Instead of the 2/4 power, it was the same as 1/2. And so now these no longer share a common factor. And so this is considered simplified at this point. Okay? Okay, so let's go back. And let's look at ones where we have some fractions. Okay, so let's try to simplify this one. So notice this is a square root, right? When we don't put a number here, it means it's the square root. So the index is 2, but the exponent here is 3. And I'm going to go ahead and factor 9. You should always factor any numbers under radicals to its prime factorization. So in this case, it would be 3 times 3. So 9 is 3 squared. I'm going to write it like that. And then I'm going to write x cubed as x squared times x. Now notice these add up to 3, okay, which it should. And then the 9 I'm going to write as 3 squared. Okay, and then we're going to take the square root of that. Now, it's the case that you can break this up into the square root of each of these. And maybe I should do this one step at a time. You can actually take the square root. So, I think I've mentioned this a couple times. The nth root of a over b is the same as the nth root of a over the nth root of b. That's a property of radicals. And in one of the previous problems, we had the nth root of a times b, and you can break that up and write it as the nth root of a times the nth root of b. And so that's what I'm doing here. I can break this up into the square root of the top divided by the square root of the bottom. Okay, so I'm going to write it like that. The square root of the top divided by the square root of the bottom. And then this can be broken up using this property into the square root of the first one times the square root of the second one. Okay, so I'm just using both of those properties to break it up into these square roots. Now the reason I'm doing that is because this can be simplified, right? Remember, this exponent has to be less than the index, and it's not. So that can be simplified, right? That's just equal to x. But this one's simplified because 1 is less than 2, right? So the exponent is less than the index. So that one's simplified. That's just square root of x. This bottom one is not, because 2 is not less than the index, 2. But that's just equal to 3. Okay, so let's go back and check and make sure that's considered simplified. Okay, so we've already checked that all the exponents in the radicand are less than the index. No fractions may appear in the radicand. So the only radicand we have is x, and it's not a fraction. Now originally it was, right? So originally the radicand was a fraction, so that's not considered simplified, but this is, right? The only radicand we have is x, and that's not a fraction. Okay, so let's look at the second condition, or third condition. No denominator of a fraction may contain a radical. So we do have a fraction here, but the denominator of our fraction is not a radical, right? It's just 3. So that's okay. Now, notice this would not have been okay. This is a fraction with a radical in the denominator, and so that's not considered simplified. Okay, but this is. Okay, and then the fourth rule is the exponents in the radicand may not share a common factor with the index. So let's check that. So this is a square root and this is a 1. Those cannot share a common factor, the index and the power in the radicand. And they don't share a common factor. So that's considered simplified. Okay, and so let's look at B now. So this is certainly not simplified. You can't have radicals in the denominator for sure. So let's try to simplify that. So again, I'm just going to go through. We're taking the cube root in this case, so I'm going to take this x to the 7th power and write it as x cubed as many times as I can. And I can do it twice, and then I'm left with one more x, because this has to add up to 7. All right, 6 plus 1, so that'd be 7. Okay, the 3, you factor the 3 into its prime factorization, which you can't do anything more, it's 3. And then the y, I just write as y to the 1st. Okay, and then on the bottom, I'm going to factor 81 into its prime factorization. 81 is 9 times 9, and then each of these are 3 times 3. And so you can write 81 as 3 to the 4th power. Okay, you can't do anything with that x, but you can write the y to the 4th as y cubed times y. And then now we're going to go through and just break this up into a bunch of cube roots. The cube root of 3, the cube root of x cubed, the cube root of x cubed again, the cube root of x, and then the cube root of y. And remember, we can do that because of this property. Okay, same thing on the bottom, cube root of 3 to the 4th, and actually what I'm going to do is write that as 3 cubed times another 3, okay, because I want to match the index. So I can write it as 3 cubed once, and then I'm left with 1 3, because those exponents would add up to 4 now, right? But then I'm going to break this up into 2 radicals, right? So I'm going to write it as cube root of 3 cubed times the cube root of just 3. Okay, and then the cube root of x, cube root of y cubed, and then times the cube root of y. Okay, so let's see if we can't simplify this. All right, the cube root of 3, this power is less than the index, so you can't simplify that. This one you can, that's just x. That's just x. This you can't, right? The index, the power is less than the index. And this one you can't either. Okay, down here, this can simplify to 3. This you can't simplify because the power is less than the index. So you just have to leave that as cube root of 3. Can't simplify this because this is power 1, which is less than the index. This one you can, that's just y. And then this one you can't because, again, the power here is less than the index. Okay, so that's how those would reduce. Now notice here, this cube root of y would cancel with this cube root of y. Those are equal. So that cancels to 1. So those cancel out. The cube root of x cancels with this cube root of x. So those cancel out. And then the cube root of 3 over the cube root of 3 is also 1, so that cancels out. And so it looks like you're just left with x squared, x times x, which is x squared over 3. Okay, and so now this is considered simplified. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.